Good morning, students. In the last class, I discussed about the physical properties of the D and F block elements and also the ionization, the periodic difference, that is especially the ionic and atomic radius and also electronic configuration of the D block elements. So in today's class, I am going to discuss about the next periodic property, that is ionization enthalpies. Ionization enthalpies. So students, in this part, we are going to study the different series are there, 3D, 4D, 5D, 6D series, and those series, what happens to the ionization energy, whether it follows the trend or not. Okay. So first I write and consider students, for example, any one of the metal is there. If it loses one electron and forms positive ion, that is unipositive ion. So this is called as what? Ionization energy 1. Okay. So what is ionization energy means? The amount of energy required to remove the electron from its valence shell. Okay. The amount of energy required to remove the electrons from its valence shell is called as what? Ionization energy. So this is the atom, the gaseous isolated atom. From here we have to remove one electron, then it will form M plus 1 unipositive ion. So that is ionization energy 1. Okay. Next, M plus 1. If it is subjected to remove another one electron, okay, then it forms pi positive ion. Okay. Then it is a bivalent ion. Then it is IP2. Okay. Similarly, keep on moving. If M plus N minus 1 ion is there, M ions are there, not N minus 1, N plus 1 you got. Charge is there, then an electron will go, right? Minus 1 charge is there, an electron left, so M, plus 1, you have to remove an electron, that is plus 2, N plus 1, N minus 1, N minus 1, minus 1. Okay, that is correct. So then we will get IEN. This is a successive ionization energies. Okay. So students, if we consider this one as an atom, for example, M, its atomic number is 17 assume. Okay. 17 means, are you assuming this M is a Cl atom? Just assumption I am telling you. This is, you take fluorine, 1s2, 2s2, 2p5 students. Okay, you take fluorine here. This is nucleus of fluorine. This is 1s orbital. This is 2s and 2p subshell. This is K subshell. This is L subshell. So here, if its atomic number is 9, here 9 protons are there. You just remember protons. Here 9 protons are there. Here 2 electrons and remaining 7 electrons. Here 1, 2, 3, 4, 5, 6 and 7. Okay, this is 2s and 2p orbital. This is 1s orbital. So students, what I am telling is, consider this one is I am not telling this is the metal, just for example I am taking that fluorine as an example. That is not metal, that is a non-metal, just for clarification. So M is there. Okay, in this M, one electron we remove means it will form what? Plus 1 charge. So this will charge, one electron will remove means that shows what? Plus 1 charge. Okay, instead of fluorine, you assume this one as M only. Okay, if it is a plus one charge, what happens here? The number of protons remains same. That is plus 9 only. Only the number of electrons will change. Here first 7 electrons are there. After removal of 1 electron, 6 electrons are there. So students, the attraction force between the number of protons and the number of electrons increases because your positive charge is more, negative charge is less. So all the neutrons are try to be neutral by bonding with or by satisfying the charge with the electrons. So then what happens? Here plus 1 charge results what? Here plus 9 neutrons are there, minus 8 electrons are there. If we neutralize the charges, we get plus 1. That's what means 1 proton is extra. That 1 proton creates some amount of attraction between these electrons. It tries to attract the remaining 8 electrons towards itself. Then what happens? Effective nuclear charge increases. Once the electron removes of the cation, the effective nuclear charge increases. That means shrinkage of the shell, orbital. Okay, if the shell shrinkage takes place, the size decreases. If size is less, we require more energy to break the bond. Okay, so next, second, same we are taking plus 1 ion. Then again we are removing another electron means. So then we will have same 9 protons but 6 electrons. So 2, 4, 5 electrons. 5, 6, 7. Okay. Here plus 9 is there. Minus 7 means plus 2 charge. 2 neutrons, sorry, 2 protons extra are there. Those 2 protons exert some amount of attraction force with these electrons. Okay, results in the again increase in the effective nuclear charge, results in more decrease in the size. Okay, so then what happens? If keep on moving the electrons, the size decreases. So after the removal of this complete shell, means how many electrons are there? 7 electrons are there in the outermost shell at the M plus 7 state. So complete shell removes means this become very small. So that is the reason I told you students, as the positive charge increases, size decreases. Okay, so then here the trend follows what? And always first ionization energy is less compared to second ionization energy compared to third ionization energy. Means removal of first electron is quite easy than second electron than third electron. Why? Because if we keep on removing the electron from atom means it keep on increases the nuclear charge, that is effective nuclear charge, and the size keep on decreases. If size decreases, charge increases, effective nuclear charge increases, that means force increases means we require more energy. That's why this is the trend. But this trend is not regular in D block elements or D series. Okay, why we are going to study. Okay, students, I'll go with the 3D series. Okay, so 3D series starts from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, here the configuration of this is, first I will write atomic number, this is 21, 22, 23. Listen students, these series are very important. The first one, you can easily distinguish the periodic friends by using only this. Third. Okay? If we write the configuration, I will write only valence configuration. Valence configuration. So here noble gas is there, argon 3D1 4s2. Here 3D2 4s2. 3d3, 4s2. 3d4, 4s2. Am I right? 3d1, 3d5, 4s1. Next, 3d6, 3d5, 4s2. 3d6, 4s2. 3d7, 4s2, and 3d8, 4s2. 3d9, sorry, 3d10, 4s1, and 3d10, 4s2. So students, here what happens to the ionization energy of first electron? So listen, here 2, 2, 2, 1, 2 orbitals are there. Okay. So here, as I told you, the periodic trends keep on increases for first ionization energy. As I told you students, along the group, if it is in this manner, then what happens? The size increases, sorry, size decreases. If the size decreases, then what happens to the ionization energy? Always increases. So first ionization energy always increases in this trend. First ionization energy always increases. Then, if we come to second, okay, assume after first ionization energy, the configuration is 3d1, 4s1, 3d2, 4s1, 3d3, 4s1, okay, 3d5, 3d5, 4s1, 3d6, 4s1, 3d7, 4s1, 3d8, 4s1, 3d10, and 3d10, 4s1. So this is what the electronic configuration of the species after first ionization energy, after the removal of one electron. So here what happens, students? Listen. This is unstable configuration 3d1, 4s1. This is also correct. This is also correct. But here it has 3d5, 4s0. So the second electron should remove from 3d subshell. Next again the same trend follows. Again here 3d10 configuration. Again it follows the same thing. Okay. If you draw the graph, students, what you will get? So this is ionization energy. This is atomic number. Okay. This is ionization energy for plus 2 ions. That is ionization energy 2. This is atomic number. This is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay. So here what happens to trend up to this is chromium. Again this is manganese. Next copper. Zinc. Okay. So students, from here the second ionization energy. Here I write the second ionization energy for scandium is less than titanium, less than vanadium, less than chromium. But this is greater than manganese. The ionization energy of chromium is greater than manganese. Again, this will follow the same trend. Manganese, iron, cobalt, nickel, copper, but zinc. This is the trend sequence. So why? Listen, because here we have 4s1, 4s1, 4s1 subshell. Here we have 3d5. So here again we have 4s1. So compared to this 4s1 subshell, this 3d5 subshell is very strong configuration or a stable configuration. So here what happens, students? This will follow. This is copper. This is chromium. this is manganese, and this is zinc. Okay, so what is the trend in the second ionization energy means? So here, the second ionization energy along the 3D series increases up to chromium, decreases for manganese, again increases to copper, and decreases to what? Zinc. Why it happens? Because chromium and copper have D3D5 and 3D10 configuration. They are highly stable compared to this 4s1. Okay, 4s1 is the half-filled configuration, so it easily loses one electron. Okay, this manganese and zinc consists of this stable as well as this unstable configuration means, so to attain this stable configuration, they easily loses one electron. So this is the trend, students. So in a 2 marks question, as I told you in the last class, they had asked why the size of zirconium or osmium is same. What is the reason for that? Okay, in this class about this ionization energy, they are going to ask students why the second ionization energy of chromium is more compared to manganese. Okay, or give reason. Or they may ask the second ionization energy of copper is more than zinc. Give reason. Okay, this is 2 marks question. You have to write the configuration of each chromium, copper, whatever they ask, and you have to compare with magnesium, manganese, and the zinc. Okay, so then you will get to know why this one has a high second ionization energy. Why not these two? Okay, so this is the second ionization energy trend. So after this, I will say what happens to the what is the answer you have to write for the question. Okay, so next one is, so this is a graph. Next one is third ionization energy. Okay, that is IE3. So students, I will write after IE1, sorry, IE2, the electronic configuration is 3D1 because this electron is also left. Again here 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, and 3D10. So listen, so for the third ionization energy, students, we have only d orbitals, d1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Here we have to choose, so along with that I told you, noble gas is there. Noble gas 3D1, noble gas 3D2, 3, 4, 5, 6, 7, and 8 up to 10. Here we have to check. So listen, this configuration is there, this configuration is there, and 3D10 configuration is there. We have to compare only the third ionization of these. Okay, so listen, the third ionization energy also increases along the period. Okay, only the trend varies in second ionization energy. In first ionization energy also increases along the period. In third ionization energy also increases along the period. In second ionization energy increases up to middle, increases up to middle, again decreases, and then increases at last and decreases. So this is the trend. Okay, but here increases again. Okay, so third ionization energy for scandium is less, very less. Okay, and manganese plus 3 is high, and zinc plus 3 is very high. Why, students? So listen, here scandium is there, that is noble gas 3D1. So if it loses one electron, it easily attains a noble gas configuration. And you know, to attain the noble gas configuration, an element always try to be in the stable form. The noble gas configuration is the highly stable configuration. So that is also called as octet configuration. So yes students, each and every atom wants to be stable means it easily loses one electron to attain this noble gas configuration. So that's why the scandium easily dissociates or easily donate this electron means it requires less ionization energy. And then we move means it keep on increases and it is high for what? 3d5 configuration. If it is 3d5 configuration, so compared to 3d6 and 3d5, so listen, manganese and iron is there. Manganese has high third ionization potential compared to what? This hydrogen. Okay, again the trend follows the same thing. This is not that much important, but here you have to compare 3D1, 3D5 and 3D10 configuration. So why? Because this is the stable configuration. Okay, this is the stable configuration means we require much more energy to remove or to break that stability. Okay, that's why M plus 3 ion is comparatively high third ionization energy. And last one is zinc. Again, it increases up to zinc, and zinc have very high third ionization energy, third ionization potential. Why students? Why? Because, so listen, this is D10 configuration, correct? D10 configuration means it is completely stable. Okay, it is very tough to break that stability. To break the stability, we require more energy because it is the at least after all the ionization energy is nothing but the energy required to remove the electron from the outermost shell means in that 3d10 stable configuration we require much more energy to break the bond. So that's why zinc plus 3 has very high ionization energy. Okay, this is all about the friends. Ionization energy 1, 2 and 3. Among these, so they always ask the question based on ionization energy 2, the second ionization energy. So whatever the questions they ask, I'll write it here students. Simply note. Because as I told you, this is very important. Sorry, I want this. Next I want means I want to do this much. Questions they are going to ask is question number 1. Why the second ionization potential of chromium is high compared to manganese. This is one question. And the question number 2 from this same thing is the second ionization energy of copper is higher than zinc plus 2. They are give directly these ions. Okay? Give reason. So this is the question they ask either this in this form or in this form. Both the cases they can change the ions students. But this is the question they are going to ask for 2 marks if they want to ask from this ionization potential. Okay, you have to note down this question and you have to answer. Okay, so this is all about what ionization enthalpies. So next one is another one. This is third property, ionization. First one is electronic configuration, second one is atomic and ionic radius, third one is ionization potential, and fourth one is oxidation state. Okay. So listen, oxidation state, there are two types are there. One is positive oxidation state, another one is negative oxidation state. So what when the positive oxidation shows, when we have to see the positive and the negative oxidation state means, if the number of electrons removed from the atom, then the atoms will show positive oxidation state, that those are called as what, cations. And if the electrons are added to the atoms, then we used to see the negative oxidation state, those are called as what, anions. Okay. So here, as I told, these are metals and they have to obtain the noble gas configuration because they are very nearer to this noble gas configuration. Means they easily donate a pair of easily donate electrons rather than accepting an electron. As I told you, the metals are always the positive charged species, means cations. They are unstable in the negative oxidation state. They are very stable in the positive oxidation state. Okay. So here, listen. Here, two types of shells are there. Right? One is valence shell, that is S subshell. Another one is penultimate shell, that is D subshell, inner subshell. Okay. So here what happens? It shows two types of valencies. One is a lower oxidation state as well as higher oxidation state. Okay, these D block element shows lower oxidation state as well as higher oxidation state. So I write only low and high because we don't have much. This is low oxidation state. This is high oxidation state. So listen, students. The oxidation state of the metals is equal to what? The presence of the number of unpaired electrons may be. Okay, this is equal to how much? The presence of the number of electrons, and especially unpaired electrons which are present in them. So lower oxidation means, so D block elements, as I told you, shows two types of oxidation. One is lower, another one is higher. So this low oxidation state is shown by the removal of two electrons which are in the what? S subshell, means valence subshell. So lower oxidation state of all the metals in D block is +2. That is because of what? Removal of electrons takes place from the valence shell. So that is the lower oxidation state of that one D block elements. Then as I told you, the higher oxidation state is caused by the removal of electrons from the what? D subshell. If the removal of electrons takes place from the D subshell, then it may be equal to the number of electrons present in that, or it may be equal to the number of unpaired electrons present in that. So here D1 electron is there. If we remove one more means it will show +3 state. Here 2 electrons are there. It may show +3 as well as +4. Okay, total 4 electrons are there. Again here +3, +4, +5. Total 3 + 2, 5 electrons are there. Okay, next +4, +5, +6. I forgot to write 3, +3, +4, +5, and +6. Okay. For this, +3, +4, +5, +6, and +7. Okay. So here, students, listen. +2 is there, plus 3, plus 4, but this is not stable in plus 5 oxidation state, then this is plus 6. Okay, so next one is plus 2, plus 3 and plus 4, that may be equal to number of unpaired electron as I told, and this is also plus 3 and plus 4, this is plus 1, not plus 2. Because as I told you in the electronic configuration it shows 3D24S1 as well as 3D94S2. So it shows plus 1 as well as plus 2 oxidation state, and this shows only plus 2 oxidation state as it has a high stable D5 configuration. So students, in this what happens means, I will mark some of the oxidation states here in which they are highly stable. Okay, this is plus 3 state. Okay, for this plus 4, plus 5, plus 6, plus 3. Okay, next this is plus 2, plus 7, plus 2, plus 3. This cobalt is plus 2, sorry, cobalt is plus 1, okay, plus 3. This one is plus 1, plus 4. This is plus 1 and both plus 2, especially plus 1. And this is of course plus 2. Okay, so the valencies or the oxidation state, what I marked is equal to, this is stable in what? Plus 2, lower oxidation state. Okay, the valencies are the charges. What I marked here is the students in which oxidation state these metals are stable. Okay, all are stable at their higher oxidation state as well as lower oxidation states. Okay, so in this, up to manganese, the oxidation state changes or the variable oxidation state is equal to what? The number of unpaired electrons which are present in them. Okay, after that, iron, cobalt, nickel, copper, zinc, what happens means the oxidation state of these is equal to the number of unpaired electrons or its stability of the atom. So listen, iron is stable in plus 2. I told you that is lower oxidation state, it is stable. Why it is in plus 3 oxidation state stable means, if we write our Ross diagram students, this is 3d6 configuration. So here 2 electron will present. Correct? This is 3d6 and 4s2 means. If plus 2 oxidation means s orbital will remove. Of course, this is the stable configuration. Why it is stable also in plus 3 means, if it loses 1 electron, it gives what? 3d5 configuration. The 3d5 configuration is highly stable compared to this before the plus 2 oxidation state. So both plus 2 and plus 3 iron compounds are stable. Okay, this is the way. Okay, this is our about the oxidation state. So here all the atoms which are formed by these higher oxidation states are stable. Okay, they are highly stable. So for example, what I want to say is, so listen, if any oxides are formed, any sulfides are formed, or any chlorides are formed from these elements, then they are what? So sorry, in higher oxidation state, if the oxides forms, then they are acidic in nature. If in the lower oxidation states, then the oxides are formed, then they are basic in nature. In between this lower and higher oxidation state, any of the oxidation state shows the oxides, and they form oxides means they show what? The variation in between the properties in between basic and acidic, that means amphoteric nature. Okay, if the higher oxidation state forms some amount of oxides, halides, or whatever it may be, they are covalent in nature, and these lower oxidation state elements are formed by the what? They are covalent means ionic in nature. Okay, as I told, so this is the stability. So all these D block elements are stable at their higher oxidation state. And as I told you, our oxidation state is done by the removal of the electron means the empty orbitals keep on The empty orbital availability is more. Okay, if the empty orbital availability is more means the acts as a good catalyst. Why the acts as a catalyst? You know what is the role of catalyst in the reaction? Catalyst is a chemical substance which involved in the reaction, which alters the rate of the reaction but never changes its chemical behavior. Okay, that is catalyst. So most of the things we use as a catalyst is so for in the preparation of or in the conversion of alkene to alkane, that is hydrogenation reaction, we use nickel as a catalyst. In the preparation of ammonia, we use iron as a catalyst. So in so many cases, we use palladium, platinum, copper, manganese, chromium there as a catalyst. Why? Because students, they have the capacity to attain the variable oxidation state, means they can accept a pair of electron or they can donate a electron. So listen, if it is plus 4 oxidation state, if it wants to accept an electron means it may changes to a plus 2 state or plus 3 state. It has the capacity to accept one electron to be stable. Okay, if it is in a plus 3 oxidation state, it has to donate an electron, then it loses 3 electrons, become plus 6 oxidation state, and it donate electron to the respective species. So then what happens, students? These acts as a catalyst. Why they acts as a catalyst means because they have variable oxidation states, they have the capacity to donate an electron or to accept an electron. So this is the one reason that hence why the D block elements are most preferably used as what? That catalysts. Okay. Another one thing is they have vacant d orbital. That vacant d orbital is more enough to accept a pair of electrons from any other species. Okay. So this is the oxidation state of what? D block elements. So what is the question raised from this topic is so students, one of the question I'm writing here is very, very important. Why D block elements are acts as good catalysts. Why the D block elements are acts as good catalyst? So two reasons is there. One, they have variable oxidation state. So because of the variable oxidation state, results in either accepting an electron or donating an electron, resulting in what? They act as a good catalyst. Another one is they have vacant d orbitals. Due to the vacant d orbitals, they create much more enough space for the incoming electrons from the other species, results in the reaction. Okay, so that's why they are answered what? Good catalyst. Okay, students. So this is students. Another one is trends in M plus 2 bar M standard electrode potential. Okay, as I told you, trends in trends in M plus 2 bar M standard electrode potential. So here what happens to the trends? What is the trend means? So listen, Trends in M plus 2 bar M, standard electrode potential. We have to measure the electrode potential of these elements by using electrochemical cells. I told you what is the electrode potential. Means it is the EMF exerted between the positive and the negative electrodes. Okay. So in that there are two trends are there, students. So first I draw the graph. Yes, cadmium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, so if it is taken, this is -2, next -1.5, -1, 0.5, 0, 0.5, 0.1. This is plus 1. Okay. So here what happens to the trend means this is a zero electrode potential. Okay. So here what happens? First, the ionization potential of this increases going up to 1. Again decreases for manganese. Next, again increases to copper. Next, decreases for zinc. Okay, again this is a negative value for zinc. Okay, students. So this is the trends in standard electrode potential. So this is what? Atomic number. This is standard electrode potential. Inert. Okay. So this value what happens? As I told you, M plus 2 bar M means the conversion of metal into plus 2 ion. As I told you in the second ionization energy, the second ionization energy is more for chromium, less for manganese. Again I for copper and less for zinc. This trend only I told. But as we compare to the standard electrode potential means this chromium and they are all what? Negative electrode potential. This copper has positive electrode potential. So this reason, if the electrode potential is less, students, then they have the capacity to reduce other elements. Here copper is there. Copper cannot reduce other elements. It is reduced by any of the elements. For example, iron is there. Iron can reduce copper, but copper cannot reduce iron. So for this 0 means this is hydrogen. Okay, these all elements can reduce this hydrogen, but hydrogen cannot reduce them. But hydrogen can reduce copper. This shows what? The electrode potential which metal is used as a catalyst to reduce which metal. For example, copper is there, copper and zinc is there. You know the Daniell cell, I think, students. So in that Daniell cell, copper is there, zinc is there. So copper sulfate and zinc sulfate solution is used. So here copper sulfate value is 0. Plus 0.76 the electrode potential. This one is minus 0.34. So here what happens? Solution here is minus 0.34. If it is a negative value, if it is a positive value, the reaction equivalence is Cu is there, Zn plus 2 is there. It changes to Zn plus Cu plus 2. Okay, so loss of electron means what? Oxidation. Okay, gain of electron means reduction. Okay, so here what happens? Here copper, sorry, this is iron, copper sulfate, this is zinc. It is reduced to plus 2 and it will form Cu. Okay, Cu plus 2 changes to Cu, that is gain of electron means reduction takes place. It is reduced by what? Zinc. Why? The electrode potential of copper is more, the electrode potential of zinc is less. This shows the electrode potential value that which metal can reduce the respective metal. Okay, this is the trend. Increases up to chromium, decreases for manganese, and it is highly positive for copper and decreases for zinc. This is the trend in the what? Electrode potential. This is the observed curve. So what is the calculated curve? Means this is the calculated curve. Of course, in the same way, but here they expect the trend in this form. Therefore, it will increase, but it is decreases. That's due to the reason, as I told you, it has D10 configuration, D10 4s1, D10 4s2, D5 4s2, D5 4s1. That is the reason. The second ionization energy nothing but M plus 2. So to that we are calculating what? Electrode potential. Okay, so this is our today's class. So in this they will ask only why copper has positive electrode potential or why chromium has high electrode potential compared to manganese. Why copper has more positive electrode potential compared to any other metals. Okay.